Okay, so let's come back to our lectures. Okay, so now in the last lecture, we have been talking about the Laplace transforms. Okay, so in the last lecture, we've been talking about the Laplace transforms. So basically, we were viewing the Laplace transforms as a mirror. Okay, so what happens there is that if you give me a function f of t, then the Laplace transforms is going to transform your function into another function, capital F of s. Okay, so the Laplace transform of f of the function t results in a function of s, right? So that's going to be the Laplace transform. So we're going to think of this Laplace transform as a mirror. Okay, so that means you have the function small f of t standing in front of the mirror, and inside the mirror, you're going to have the image, which is the function capital F of s. Okay, so that's going to be the Laplace transforms. Now, the Laplace transform was defined from the last lecture to be the integral from 0 to infinity e to the power minus s and t of f of t dt. Right, so that's going to be the Laplace transforms. Okay, so that's going to be the Laplace transforms, right? So that's going to be Laplace transform. Now remember here the integral is integrating on an indefinite domain infinite domain from 0 to infinity, where you're integrating with respect to t. Okay, so when you integrate t out, you're going to just be left with the variable s, and you're going to set the s as the variable for the Laplace transforms. Okay, so that's going to be the Laplace transforms. Now, the Laplace transform was introduced in the previous lecture. Okay, so the Laplace transform was introduced in the previous lecture in the sense that we see several calculations of the Laplace transform. For example, we were seeing that the Laplace transform of the function 1 is going to be 1 over s. Okay, so, and then the Laplace transform of the function e power at is going to be the function 1 over s minus a, where s is bigger than a. Okay, so that's going to be the Laplace transform of e power at. Okay, so, and then we have been introducing very important property for the Laplace transform is that the Laplace transform transforms a linear combination of functions into the linear combination of their images. Okay, so that kind of helps us to calculate Laplace transforms such as 5 times e power minus 2t plus 3 and things like that. Okay, so basically we have been seeing several properties of the Laplace transforms. Okay, so we see that Laplace transform is a linear operator, and the Laplace transform of alpha f plus beta g is alpha Laplace transform beta Laplace g. Okay, it is important to realize that when you define the Laplace transforms, the argument of the Laplace transform is limited. Okay, so it's not with respect to arbitrary s, but you must set s to be positive. So this is going to be important that at least the argument s is positive, but it might be even more than positive, as we saw in the last lecture. Okay, so as we saw in the last lecture, that when s, okay, so when we're talking about the case when you transform the function e power of at, then the Laplace transform is going to give you 1 over s minus a. Okay, so that's going to be the Laplace transforms for the linear operators for Laplace transforms. Now we see several examples of Laplace transforms that are more concrete for your exams. Okay, so for example, like here, and the Laplace transform of the function sinus of at. And in these cases, you can see that when we were calculating the Laplace transforms, it is very important. It is very important to realize that you must use at some moments integration by parts. And when we were calculating the Laplace transform of sine at, we've been using 2 times the integration by parts. Okay, so we've been using 2 times the integration by parts. Okay, so that's going to be the Laplace transforms business. Okay, Laplace transform business. Now, starting from this lecture, we will be studying solving the initial value problems. Okay, so that's differential equations and initial value problems. Okay, so differential equations and initial value problems. Okay, so we will be solving differential equation and initial value problems. using the Laplace transform. So how are we going to do that? Well, the basic idea is the following. So if you have a differential equation, okay, so if you have a differential equation, like any kind of equation that you see, okay, so any kind of equation that you see in this lecture, then under the Laplace transforms, the differential equation is going to be transformed on something. So presumably, our goal is to solve this differential equation on the left side, but if you cannot solve them, we're going to solve their corresponding equation after the Laplace transforms. Okay, after the Laplace transforms, we solve this object, and once you have this object, it corresponds to a solution to the differential equation. That's the rough idea. Okay. Now, presumably, you can see that differential equations, let's say, is for a function f of t or maybe y of t. You're trying to solve a function of t, but it always involves the derivatives of f, such as f prime, f second derivative, etc. So it must involve y prime, y second derivative of t, etc. So therefore, if you want to Laplace transform everything, you just want to understand Laplace transform of f, Laplace transform of f prime, Laplace transform second derivative, etc. Or maybe same thing as Laplace transform of y, Laplace transform of y prime, and y second derivative, etc. Right? So therefore, it is important to understand how to calculate Laplace transform over derivatives. Is that good for everybody? Okay. So now let us try to compute the Laplace transform over derivatives. So that means we would like to start from calculating the Laplace transform, let's say, of f. Okay, so f prime of t. Okay, so f prime of t. So now, in order to be more precise, in order to abbreviate, I will just say Laplace transform of f prime, which means that this is actually the Laplace transform of f prime of t evaluated at point s. Okay, so that's going to be the Laplace transform. Now, by definition, the Laplace transform is by definition the integral from 0 to infinity e to the power minus s and t multiplied by, now it's f prime of t, because you're just trying to do the Laplace transform of f prime. Okay, so you're just trying to do the Laplace transform of f prime. Now, if that is the case, you can immediately recognize that you're able to use integration by parts in order to calculate the whole integral. Okay, so you're able to use integration by parts in order to calculate the whole integral. Now, if you would like to use integration by parts, then you are going to see that you will treat it, you will be working with e power minus s and t multiplied by f of t, where t is equal to infinity and t is equal to 0. Okay, so these errors between the two, right? So between the two, and then it is a minus, right? So because of integration by parts, you're going to do minus the integral from 0 to infinity. So therefore, by the integration by parts, we're going to take derivative of e power minus s and t with respect to t. So that's going to end up with minus s e power minus s and t, right? So multiply by f of t, integrate against the dt, right? So you get this is basically integration by parts, right? So let's say this is basically integration by parts. Okay, so by integration by parts, you're going to have this. Now, once you have this, it means that you have e to the power s multiplied by infinity multiplied by f at infinity minus e to the power s multiplied by 0 multiplied by f at 0. And then there are two minuses, so that's a plus. So I will pull s out, integral 0 to infinity minus s and t f of t dt. So why you can pull the s out? Because here we're integrating against the t, so that s can be treated as a constant. Okay, so s can be treated as a constant. So that's why you have s multiplied by the integral. And then you can see that because usually in the Laplace transforms, we're going to assume that s is positive. Okay, so if s is positive, you're going to see that limit as u goes to infinity, e to the power s multiplied by u is going to be just 0. Is that good for everybody? Okay, so because of this, this term is going to not going to appear in the calculation, right? So, and what about this term? Well, e to the power s multiplied by 0 is e to the power of 0 is just 1. So there you don't have this term. And what about this term? Well, this term exactly is the Laplace transform of f. Or maybe more precisely, it's the Laplace transform f of the function t and result in the function s. Is that good for everybody? So therefore, we can see that this is actually the Laplace transform of f multiplied by s minus f of 0. So you get a very important identity. Okay, so you get a very important identity saying that Laplace transform of f prime is s times the Laplace transform of f minus the f of 0. Is that good, family? Okay, so that's you get such a very important identity. The Laplace transform of f prime is s Laplace transform of f minus f of 0. Okay, so therefore you can see that now we are really able to calculate the Laplace transform of the derivative. Okay, so we're really able to calculate the Laplace transform of the derivative. Now the question is, for example, are you able to calculate the Laplace transform of the second derivative? Well, here you might say, well, that means I want to calculate minus s and t multiplied by the second derivative of t dt, something like this. And then I'll do the calculation, right? So, well, you can do it in this way, but since we know the Laplace transform of the derivative, we can do everything in an inductive way, okay? So how to do things in an inductive way? Well, in an inductive way, that means you're going to replace f by f prime here. So that means this is s L f prime minus f prime of 0. And if that is the case, the Laplace transform of f prime is s times Laplace transform of f minus f of 0 minus f prime of 0. So you're going to result in an s square Laplace transform of f minus the s of f of 0 minus the f prime of 0. So that's going to be the Laplace transform of the second derivative. Okay, so now you can continue this business. For example, I'm asking you, what is the Laplace transform of the third derivative? Now you can see that you can just use this second derivative so that you can see that this is s squared. Okay, so let me use the second derivative first. So that means this is s times the Laplace transform of the second derivative minus the second derivative at point 0. Is that good for everybody, right? So you just use the treat second derivative as the f, then you're going to take one more derivative, which is the third derivative. Now you can use the second derivative formula here, so that you're going to have s squared, the Laplace transform of f, minus s f of 0, minus the f prime of 0, minus the f second derivative of 0. So you're going to end up with s cubic Laplace transform of f, minus s squared f of 0, minus s f prime of 0, minus s f second derivative of 0. Is that good for everybody? Okay, so you get such a chain of inequalities. Okay, so let's re-summarize these inequalities. You can see that this forms a certain kind of a tower. Okay, so a tower of identities that has some kind of underlying rules. Okay, so for example, you're going to see that Laplace transform of f prime is equal to s Laplace transform of f minus the f of 0, and Laplace transform of f second derivative is equal to s squared Laplace transform of f minus the s, okay, so of f of 0 minus the f prime of 0, and Laplace transform of f third derivative, right? So third derivative is equal to what? Well, it is equal to s cubic of the Laplace transform of f minus s squared f of 0 minus s f prime of 0 minus f second derivative of 0. Is that good for everybody? So it is easy that you can just kind of guess, right? So what is the Laplace transform of the fourth derivative? Well, it's just s to the power of 4 Laplace transform of f minus s cubic. Okay, so f of 0 minus s squared f prime of 0 minus s f second derivative of 0 minus f cubic derivative at point 0. You can just do things in this way. Okay, so you can just do things in this way. And you can continue. Is that good for everybody? Okay, so that's going to be how you calculate the Laplace transforms of the derivatives. So what is the in general? Okay, so what is in general? Well, in general, you're going to see something like this, right? So in general, you're going to see a theorem, something like this, that the Laplace transform of nth derivatives are going to be resulting in a formula like this, right? So in general, okay, so in general, we are going to see that Laplace transform of the nth derivative is just going to be, you can see that these are powers of s, right? So that's going to be s to the power of n of the Laplace transform of f, and minus the s n minus 1, starting from the n minus 1, you're going to have n minus 2 f prime of 0 minus the s of, I mean, you can continue these minuses, right? So until you reach s times f of the n minus 2 of 0 minus f of the n minus 1 of 0. Is that good for everybody? Okay, so now first of all, let us kind of observe the rules, underlying rules behind these formulas. Okay, so what happens here is that you're going to have, first of all, an increasing power of s. And then each of this resulting right-hand side can be treated as a polynomial in S. It's just the coefficients are f of 0, f prime of 0, f second, etc. Okay, but the leading polynomial is not a coefficient, but a function. So it's s to the power of n multiplied by the Laplace transform of f. Okay, and the remaining terms are, you must remember that the remaining terms are organized in the following way, that the numbers of powers of s plus the number of derivative of f, when you sum together, it is always equal to n minus 1. Like here is the power of n minus 1, derivative is 0, power is n minus 2, derivative is 1, etc. Is that good for everybody? Okay, so that's going to be how you calculate the Laplace transforms. Now let me make a few remarks here. Okay, so my remark is about differential equations. Okay, so imagine that you are solving a constant coefficient equation like what we see before. Okay, so it's equal to 0. Then you can see. Okay, so then you can see that you're doing a certain transformation, although it's not Laplace transform, but you're going to say that y is equal to e power of rt. And because of this, this equation is now replaced by the characteristic equation ar squared plus br plus c is equal to 0. That's exactly what you do in your calculus. I mean, in the previous chapters, right? So now, why is this the case? Well, because y. Okay, so if you have y equal to e power rt, then y prime is r times y, right? So and y double prime. Okay, so is r squared times y, etc. So basically, in general, the nth derivative is r to the power of n multiplied by the original function. And it's only because of this that you can actually reduce the the differential equation to an algebraic equation in terms of y. Is a good family. Now you can see that for our Laplace transforms, you have actually very general like f n derivative. Presumably should be s to the power of n multiplied by Laplace transform of f. This will be the case like what happened here. Is a good family, right? So that's basically is kind of very similar to what happened here. Is that r to the power of n is like s to the power of n. However, our situation is not so ideal. This is the ideal case, right? So, which is not the case, right? So, but rather what we proved is that there is a leading term is correct, but then starting from the next term, you are going to have some kind of annoying trash terms here. Okay, so Sn minus 2, like f prime of 0 minus dot 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 minus s. Okay, so f of the n minus 2 of 0 minus f of the n minus 1 of 0. So that's going to be the remaining terms. Okay, so the remaining terms, they are not the trash terms, but we're going to call them the reminder terms for initial values. Okay, so that's we're going to call them okay, so we're going to call them reminder terms. Okay, so we reminder terms for initial values. Now you can see why they are for initial values. Well, that's because when you use, okay, so according to our paradigm at the beginning of this lecture, we're trying to solve differential equation using a Laplace transform. And if you want to do that, then these terms are going to be those initial values because this f of 0, okay, so because this f of 0, f prime of 0, etc. are the initial values. Is that good, family? Okay, so we're going to use them for the initial values. Okay, so that's kind of the real idea how you're going to use the Laplace transforms to solve this differential equation. The crucial thing is to remember that you have certain rules. Is that good, everyone? Okay. So now this is with this given, let us try to see how to realize our idea, right? So we are trying to kind of use the Laplace transforms to solve a certain initial value problem. Okay, so therefore let us look at this initial value problem. Okay, so this initial value problem here. Okay, so let's look at this initial value problem here. Okay, so let's try to make it here. and try to solve it. Okay, so we are going to have a certain initial value problems like this. Okay, so we're going to have a certain initial value problem like this. Okay, so how are we going to solve it? Well, of course, you should apply. Well, our idea is to apply the Laplace transform on both sides of this equation. So that means the Laplace transform of y double prime minus y prime minus 2 times y is going to be the Laplace transform of 0. Is that good for everybody? Okay, Laplace transform of 0. Now the point is, what is the Laplace transform of 0? Well, if you calculate the Laplace transform of 0, it is going to be the integral from 0 to infinity e power s and t multiplied by 0 of dt. Because you have 0, this is going to be 0. So indeed, the Laplace transform of 0 is 0, although the Laplace transform of 1 is not exactly equal to 1. Is that good for everybody? Okay. Now, what about the left-hand side? Well, because the Laplace transform of linear operation, that's why we have been introducing the linearity of Laplace transforms, because you can split the bracket into L y double prime minus L y prime minus 2 times L of y is equal to 0. Because that's because the Laplace transforms is a linear operation, alpha of f plus beta of g is equal to alpha of the Laplace transform of f plus beta of the Laplace transform of g. Is that good for everybody? Okay, so that's going to be a linear operation. Now, because of this, you can now start to use you can see that you have the transformations of the derivatives. You can now start to use the formula that we have just obtained. Okay, so if you just remember them, now I'm replacing the f by y. What is the Laplace transform of y prime? Well, it is equal to s times the Laplace transform of y minus the y of 0. And what about Laplace transform of second derivative? Is s squared Laplace transform of y minus s of the y of 0 minus the y prime of 0. Is that good for everybody? Okay, so is that good for everybody? Now, if you have these cases, then this s Laplace transform of y minus y of 0 is equal to 1. So y of 0 is 1. And this one is s squared Laplace transform of y minus y of 0 is 1. So s minus y prime of 0 is 0. You're going to have something like this. Is that good for everybody? Okay, so you can see that you are able. Okay, so basically you're able to represent any of this Laplace transform of the derivatives as the s to a certain powers multiplied by the original Laplace transform. So if you have all these things there, then it means that s squared Laplace transform of y minus s minus the Laplace transform of y prime is s Laplace transform of y minus 1 minus 2 times the Laplace transform of y is equal to 0. Is that good for everybody? Okay, so you get this. Now, as long as you have this, it means s squared minus s minus 2 of the Laplace transform of y, it is going to be s, okay, so minus 1, because you have minus s, you have plus 1, so you have s minus 1. So that's going to tell you that the Laplace transform of y is equal to s minus 1 over s squared minus s minus 2. Is that good for everybody? Okay, so that's going to be the case, how you calculate the Laplace transform of y. Now, let us summarize this idea as a picture. Okay, so let us summarize this idea as a picture. So you can see that Laplace transform, right? So originally, on the left-hand side, you have the differential equation y double prime minus y prime minus 2 times y is equal to 0 with the initial conditions. So the Laplace transform deals with initial conditions immediately. Okay, so it deals with the initial conditions immediately, which means that y0 is 1 and y prime of 0 is 0. Okay, so you're going to deal with the initial conditions immediately. Okay, so now this equation is standing in front of the mirror of Laplace transforms. Okay, so that's going to be transformed to something. Now, when you are transforming, this equation now becomes s squared minus s minus 2 of the Laplace transform of y is equal to s minus 1. So you are really able to solve this equation inside the mirror because you don't have any derivatives. So that's the good thing. Okay, so because you don't have any derivatives. So that's the good news. Why you don't have any derivative? Because this transformation is going to, this identity about transformation is going to help you get rid of any of those derivatives and recover the original Laplace transform. Right, so you are really able to get rid of any of those derivatives. And moreover, you can see that unlike the characteristic method always gives you something like yt is c1 y1 of t plus C2 y2 of t, and you have to kind of determine the constants C1 and C2 from the initial conditions. But Laplace transform method is kind of this. Let's say this is the initial value problem. The Laplace transform method is kind of different. It doesn't really calculate any of the C1 and C2, but it results in the Laplace transform of the initial value problem immediately. Is a good family? Okay, so that's kind of the idea, is that the left-hand side is a differential equation. Now, after the mirror, the Laplace transform is going to transform the differential equation into an algebraic equation. And you can easily solve this algebraic equation. You obtain the Laplace transform of the unknown function. Is that good, family? Okay. So now, is this the end of the story? Well, this is not exactly the end of the story, because once you know the Laplace transform, so that basically what you want to do is that from the Laplace transform, okay, so let me erase this because this is for our previous method, okay, so it's not for Laplace transform. Now, once you know the Laplace transform, you want to calculate y, right? So because this is exactly what you have to come back to the real world, right? So you cannot always live in the mirror. That's only the images of the Laplace transform, but you want to solve what is y. Is that good for everybody? Okay, so here comes a problem. So that means the y, let's say, suppose the y of t is given by a function f of t. Then you are facing the following scenario. You want to calculate a certain function f of t such that the Laplace transform of the function is a given function capital F of s, which is the capital F of s here. Is that good for everybody? Previously, we were talking about forward transformations. That means you're giving me small f, you can calculate capital F. But if you're giving me capital F, how do you calculate small f? Okay, so this is going to be a very important issue here that we call it the inverse Laplace transforms. Okay, so the inverse Laplace transforms. Okay, so that's going to be the inverse Laplace transforms. Okay, how are you going to define the inverse Laplace transform? Well, the inverse Laplace transform are defined easily. Okay, so basically it says that if the Laplace transform of small f is equal to capital F, then the inverse Laplace transform of capital F is equal to small f. Is that good, family? Okay, so basically you're going to have the following picture, that you have a small f of t under the Laplace transform is going to be transformed to capital F of s. And therefore, if you have capital F of s, then the inverse Laplace transform is going to transform you back to f of t. Is that good, family? Okay, so that's kind of the inverse Laplace transform can be defined easily. Okay, so basically L inverse of capital F of s is equal to small f of t if, okay, in Laplace transform of f of t is equal to capital F of s. And if and only if. Is that good, family? Okay, so you have this inverse Laplace transform. Now, can we calculate the inverse Laplace transform? Well, the answer is yes. Okay, so the answer is yes. You can calculate some of these inverse Laplace transforms. For example, we've been seeing that Laplace transform of 1 is equal to 1 over s. Is that good, family? Okay, so from here you can see that the inverse Laplace transform of 1 over s is going to be 1. So that's how you're going to calculate the inverse Laplace transform. For example, we calculate e power of at is 1 over s minus a. So therefore, the inverse Laplace transform of 1 over s minus a is e power of at. Is that good, family? Okay, so remember here s is positive and here s is bigger than a. And same thing as that we calculated sinuses of at, it was resulting in a over s squared plus a squared, which means that the inverse Laplace transform of a over s squared plus a squared is equal to sinuses of at. So that's going to be like the relations between the forward and inverse Laplace transforms. Is that good, family? Okay, so the inverse Laplace transform can be kind of obtained by what we have been calculating up for the forward transformations. Is that good, family? Okay, so in fact, in your textbook, okay, so in your textbook, there is going to give you a table, okay, so about the Laplace transform. So what happens here is that in this table, the first column are the function small f of t, and the second column is the function capital F of s. Okay, so you can see that y is transformed to 1 over s, as we see before. E power at is transformed to 1 over s minus a, as we see before. But you have many other functions that has already been calculated. For example, sinuses of AT is going to be A over S squared plus A squared. This is what we have calculated. Cosinuses of AT that I left to you as an exercise, you're going to result in S over S squared plus A squared. What about sine H and cosine H? Well, the sine H and cosine H are the hyperbolic sine and hyperbolic cosine. So basically, sine H of x is equal to e to the power of x minus e to the power of minus x divided by 2, and cosine H of x is equal to e to the power of x plus e to the power of minus x divided by 2. How to memorize this? Well, just remember that sine H is like sine, that it is an order function, so it's sine H of minus x is equal to minus sine H of x. Cosine H of minus x is equal to cosine H of x. So that's going to be like the very simple, okay? So very simple relation that just following the even and oddness of sine and cosine. Is that good for everybody? Okay, so you're going to have this very simple, okay? So very simple relation. So this table is going to be kind of very important, okay? So this table is going to be kind of very important that I would like to remind you that if you go, okay, so if you go to your Canvas webpage and you click courses, okay, so you click courses and you click all courses, okay, so you click all courses and browse more courses, then you're going to see on the student resources webpage, okay, so then you're going to see on the student resources webpage a short table of Laplace transforms. Okay, so this is going to be the Laplace transform that will be attached to your exam. Okay, so that will be attached to your exam when you go to the exam room. Okay, so this is going to be the table of Laplace transform that you're going to see on the exam when you go to the exam room. Okay, so let me show you my table here, which is just exactly the same as this table. Okay, so as this table. Okay, so here. Okay, so Laplace transform short table. Okay, so this is the table that it will be attached. It will be attached to your exam paper starting from the next exam. Okay, so you can see that besides the index column, the first column are the functions small f of t, and the second column are the capital F of s. So one is transformed to 1 over s, as we see before, e to the power of at, this one we see it, sine we see it, right? So it's just b is a is replaced by b. Is that good for everybody? Okay, so, but you see many rows. And you also see that actually what we have been learning in today's lecture is also shown here. F prime of t is transformed to S Laplace transform of Laplace transform minus f of 0, f second derivative and nth derivative. So you can actually use these formulas when you're on an exam. So these are given. Okay, so remember, in this course, a lot of those formulas are not given and you have to memorize them, but these formulas are really given. Is that good for everybody? Okay. Now, for in a certain sense, the rest of the, this chapter is about this table. So we're going to carefully study each row of this table and study how to use them. And remember that when you use this table, you can go either forward or backwards. So that means, for example, you can calculate forward transformation, but it also implies the backward transformation. Okay, so you can go either forward or backwards. Okay, so that's you have several ways to go. Okay, so either forward or backward direction. Okay, so this is going to be a very important table that you're going to make full use of throughout the semester and throughout the exams. Okay, so that's why please go to the Canvas and take a look at the student resources and find this table of Laplace transform there. Okay, so it will be very important for your future study of this class. Is that good for everybody? Okay, so that's probably all I want to say for today's lecture. Let us finish here and let us come back to our lecture for the next time. Okay, so see you in the next lecture.